Hello, everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Professor Sergei Kalinin, who is a Western Fulton Chair Professor at the University of Tennessee, Knoxville. In 2022 and 2023, he has been a principal scientist at Amazon Special Projects Moonshot Factory. Before then, he has spent 20 years at Oak Ridge National Laboratory, where he was corporate fellow and group leader at the Center of Nanophase Material Sciences. His research focuses on the applications of machine learning and artificial intelligence methods in material synthesis, discovery, and optimization, automated experiment, and autonomous imaging and characterization workflows in scanning transmission electron microscopy and scanning probes for applications, including physics discovery, atomic fabrication, as well as mesoscopic studies of electrochemical, ferroelectric, and transport phenomena via scanning probe microscopy. Sergei has co-authored more than 650 publications with a total of around 55,000 citations and an H index of 115. He's a fellow of AAS, RSC, AAIA, MRS, APS, IOP, IEEE, Foresight Institute, and ABS, a recipient of the Feynman Prize of Foresight Institute in 2022, Blatnik Award for Physical Sciences in 2018, RMS Medal of Scanning Probe Microscopy in 2015, a Presidential Early Career Award for Scientists and Engineers from PECASE in 2009, Burton Medal of Microscopy Society of America in 2010, and 5 R&D 100 awards from 2008 up to 2023, and a number of other distinctions. Sergei, thank you so much for joining us today. Thank you so much for your time. And with this short introduction, you can start whenever you're ready.
Thank you very much for the introduction and the invitation. So as advertised, for about 20 years, I worked at Oak Ridge in the Nanoscale Science Center, where I built one of the first programs in the DOE system combining machine learning and the experimental sciences. Then, as many people before me, I decided that user programs is a great place to be for the first half of your career, but maybe not till the end of it. So I decided that it's time to move to the University of Tennessee, especially given that I had multiple appointments and mentored students and served as the PhD advisor to students for almost 15 years by now. So the only unusual step in this transition was that I decided that I want to look at the real world. And I spent a year almost like a sabbatical in the Amazon Grand Challenge division. So that's a small part of Amazon that's dedicated on the moonshot projects, sort of roughly equivalent to the Google X. So very interesting opportunity to look at the world more from corporate and business perspective. So the reason why I'm very excited to give an opportunity to share the problems that I work on is because, first of all, they may resonate with the optimization and PIN community. And secondly, because I believe that we are now in a very unique point in the development of the material science. And the previous inflection point like this was about 40 years ago when the personal computers appeared. So material science cannot change overnight, but what's happening now comes very, very close. So let me show what is going on and why I believe that the combination of the optimization and the automated science can make this change. So kind of another way to introduce this topic is with the quote from the Oppenheimer movie that the theory or machine learning can get you only so far. So at some point, we actually need to make things for them to become useful. Just predicting and just calculating stuff is not enough. So at UT, there is a fairly long tradition of the automated experiment. So, for example, some of my colleagues worked in the area of the combinatorial growth and even combinatorial processing for more than 15 years. And University of Tennessee was one of the first places in the US that started the robust program on the automated synthesis. So you have seen the example of the automated robot synthesizing materials 5 years ago. So this is a relative newcomer, the robot that synthesizes films inside the glove box. So you can make solar cells and you can make batteries and whatever. So once I joined the University of Tennessee, my focus was on the developing of the program, interfacing the characterization tools and the ML. So my own group works on the integration between the scanning probe microscopy and machine learning agents, and I'll show what are the principles beyond this integration. My colleagues work on the automated electron microscopy. So you can see an example where we use the electron microscope as the essentially atomic 3D printer. So if you look at this movie, you can see that these are the small dots are silicon atoms. This region is the amorphous silicon. So what we are doing is we are using the electron beam to recrystallize amorphous silicon into crystalline silicon, and we do it with atomic scale precision. So it's the way to think about it is essentially 3D printing on the atomic level. And we get a very strong buy-in from the University of Tennessee leadership for going forward with building the automated control for X-ray machines, non-indentation. Some of my colleagues work on the polymer flow systems. So in other words, a lot of scientific tools that operate in the lab by now are either automatable, meaning that they have the APIs that allow to deploy machine learning workflows, or they can be hacked into in a way that is almost doable and relatively safe. But the key challenge here is how we're going to make it all work together and produce some useful outcomes. So why is it difficult? So let's look at how the machine learning started to integrate into the chemistry, material science, physics, and so on and so forth. So the big inflection point for that was the year 2006. One reason was that was the Gersider paper in the Nature Materials, which essentially launched the Material Genome Project. The second reason was that 2006 is when the AWS basically advertised the cloud computing. So the advent of cloud computing means that if now you want to build a software-based business, or if you want to scale your computation, you don't need to build a cluster. You just need to be able to pay for the cloud compute. So this was almost 20 years ago. For the last 20 years, the field was growing almost exponentially. So all of you have probably seen the recent papers from Microsoft, Google, and so on, when they started to shift towards machine learning for science. But there is one very important aspect about this machine learning workflows. So in general, all of them start like this funnel type of character. You start with some search space. It can be the latent space of autoencoder. It can be the space over which you have the operating genetic algorithms. It can be the space in the sense of just a list of the materials that are commercially available. Then you apply the set of progressively more complex filters. Then you come up with a small number of candidates. You may estimate the synthesizability scores, but then you pass them to the experimentalist and you say that the theorist's work is over. So from this point of view, experiment is always becomes a validation. That's absolutely not how the science works. So in science, we perform the experiment based on the theoretical prediction, but then we analyze the results of the experiment, and we need to build the feedback back to the theoretical model. Obviously, we cannot do it for the DFT. We are not going to change the DFT models based on the result of single experiment, but the need for experimental feedback from experiment is there. So in the experiment, the experimental workflows were developing very rapidly, starting from about 2020, and the workhorse for those is essentially myopic optimization method. So typically it is Bayesian optimization on top of some form of the Gaussian processes. So you start with some parameter space, you perform some form of measurement over there, you figure out what is that about that measurement that you care about. So very often you measure spectrum, but you say that I care only about the position of the peak or the intensity of the peak. You build a surrogate model that allows you to calculate the prediction and uncertainty over this parameter space. And then you form your acquisition function, which defines the policy on how you select the next point. And then you go in circles, and that's how experimental workflows by now are operating. This is very, very different from how the experimental science works in general. So even if you have a relatively small material synthesis lab, the workflows that appear in the context of the synthesis and characterization are far more complex. So imagine that you start with some set of reagents. You can use them to use these robots that I've shown to make the microcrystals. Or you can use another robot to make thin films. Or you can grow single crystals, so that one you do without robot, you need to do it manually. Then for all type of synthesis, you need to have some form of characterization. So optical properties, microscopy, spectroscopy, you can build the device and characterize the device behavior. And the decision-making in the lab is based on the multiple feedback loops. So for example, we can create microcrystal library, explore the stability, and then choose the materials for the thin films based on this microcrystal characterization. Why would we do that? Because this takes an hour and this takes a day. So the use of the multi-fidelity scheme to accelerate the discovery of films based on crystals makes sense. And that's a relatively simple by now problem. But very often we get the data, for example, cathodoluminescence or TOF or whatever, which is essentially spectra or images. And once we have this data, we want to make a decision of how do we change our processing pathway, or even what other reagent do we choose. So in other words, we deal with the multiple levels of decision-making that we make based on the perceived gain, latencies, cost. There are multiple iterative cycles. And the problem is that that's not a single optimization cycle, and it's not a single workflow that I've shown. So this type of problems are absolutely universal. So if we show that, for example, this is a development of the material inside the lab, this is the transition to the device prototype, and this is the transition to industry, we can always say that here the feedback cycles are usually relatively fast, and we generate some form of the functional foundational knowledge. Once we move from the lab to the fab, the optimization cycles become much slower, and the processing dimensionality and complexity of the parameter spaces become much larger. So here we can rely on data. Here we rely on the heuristics and the prior knowledge. At the same time, the value propagation typically goes from industry back into the fundamental science. So we sort of create the economic impact only on this stage. So to summarize it, we often deal with the scientific data, which is high dimensional. The value can be understood only down the line, and the real world R&D always involves multiple coupled exploration loops. So the question is, can machine learning and physics be enough to help us integrate across these scales? And one thing that I want to pose that absolutely not. So imagine that we show the physical and database methods as two nodes, two corners of the triangle. So here we have the big data methods all the way from DCNNs, LLMs, and so on. Here we have physics, so analytical theory, computational experiments, and so on. Somewhere in between, we have the things like pins, structural Gaussian processes, neural operators, and so on that combine physics and data. So what would be the third corner of this triangle? The third corner is a reward. So typically, no matter what we do, we have some goal in mind. For example, if you work in the climate tech, what you want to do is address the global warming. If you work in battery industry, you want to make a better battery materials. Obviously, this is a reward which is far in the future. So we don't know how the specific development in the lab now is going to affect the climate tech in 20 years from now. But at the same time, the rewards that we use in physics on data science are usually much more simplistic. So prototypically in data science, we use loss functions. In physics, we use things like predictive power or parsimony of the equation as the sort of reward. So we have a lot of things in between. So materials prediction, device optimization, manufacturing, these would be the reward functions between these simplistic ones that we use now and the ones which are super complicated. Now, the question you may ask is, what does this guy even know about the machine learning? So is it some form of the edge opinion, or is it a mainstream opinion? And in principle, as the form of very strong confirmational bias, I can show you a quote from the book of Peter Norvig about the artificial intelligence, which basically in the introduction says that almost all AI research today has assumed that the performance measure, meaning the utility of the reward function, is known. The point that I want to make is that in the real world, we have a range of the possible reward functions, and we use only the most simple ones, either in physics or in the database methods. Now, the question becomes, that's a great assertion, right? But any physical theory, in order to be correct, has to satisfy at least two conditions. So condition number one, it has to explain what has been done before. Condition number two, it has to allow you to do things that has not been done before. So let's see if this reward-based concept actually allows to do that. So for me, the road towards that started from the microscopy. So I started to work on the ideas of combining machine learning and microscopy almost 15 years ago, and then I basically did it continuously ever since. And based on some analysis, we are coming up to the certain vision of how the machine learning and microscopy can be used. So on the most simple level, we use the machine learning after the data is acquired. So the second level is when we use machine learning for the real-time data analytics. So we take the multi-dimensional data sets and we present them in the form that humans can understand and make decisions based on, but the decisions are still made and orchestrated by humans. And the third level is when we have a machine learning agent that actually has access to the data streaming from the instrument and makes decisions and implements these decisions directly. So notice that there are two more levels. So these are the levels that are pertaining to the operation of the microscope as is. But we can also think about how we use machine learning for the downstream use of microscopy data and even for the upstream planning. So for example, the microscope can be connected to the material synthesis platform, and depending on the result of the experiment, it can tell the material synthesis platform what other sample to make. So this is actually not a sci-fi, this is something that we can work on. We can try to specify, so first let's look at it from the point of view of the goals. So what can microscopy do for materials? So what can be our reward function? Turns out that the value of microscopy that allows to measure things fast and that allows to measure things in the small volumes. Another value is that we can learn correlative relationship, for example, between structure and properties. And sometimes we can learn the generative physical model. So for example, if I can observe atoms on the surface, I can map these observations to something like Ising Hamiltonian to find out what are the exchange integrals in the material. So how would this reward concept work? So let me show you an example of the structure property discovery. So imagine that I have an object and this is my field of use. This is what I see in the microscope. Let's assume that I can take the spectroscopic measurements, which basically measure some form of spectrum. Currently, if we want to automate this process, we are just doing this type of measurements on the grid. But that's not always possible because sometimes measurements are destructive. Sometimes they take too much time. So the question becomes, what would it take to make the microscope automated? And then we realized one super interesting thing, that in order to make the microscope automated, we have to operate in the environment when the number of commands that we can issue to the instrument is very small. So we can tell the instrument to tune itself, we can tell the microscope to take a scan, we can take a microscope to take a spectrum. But the human logic or human reward structure involved in operation of the microscope changes throughout the experimental campaign. So in the beginning, you will optimize the microscope. After that, you are going to try to explore the regions which are statistically most present. For example, the regions with these stripy patterns. After that, we can start to explore discover the regions with interesting properties. So for example, I may want to find the microstructures that optimize the area under the hysteresis loop. And this type of problem, by the way, is kind of universal. It's the same type of problem as finding the molecular structure that has the required optical properties measured as spectrum. And after that, I can start to go to the point of physical theory falsification. For example, if I have a theory that something interesting should be happening in the regions with the elastically non-compartible domain structures, then these are the places where this can manifest. So what turns out is that the basic experimental workflow in microscopy is very simple. So you tune the microscope, get overview image, select a location, take a spectrum, do it several times. Then you can iterate over this loop, or you can take another overview image, or you can retune the microscope. So the number of commands we can issue is very limited, but the decision-making beyond those commands is very complicated and depends on operator, and it depends on the goal of the experiment, and it depends on the stage of the process. If we want to have the machine learning agent running the experiment, we need to be able to translate this operation in the language of the, if you will, reinforcement learning or stochastic optimization. In other words, we need to define the policies that allow us to do something, or we need to define the rewards, either myopic rewards or the sparse reward, and then we let our machine learning agent to learn the policies that maximize those rewards. So what can be the reward functions in imaging? So if we now look at the imaging in itself, rather than imaging in the context of material or physical sciences. So the first and most important one is imaging optimization. So we always want to make the microscope work better. It's just a part of the job. Another is the discovery of the physical laws. Then we can have multiple reward functions that can be selected based on the what we are looking at. For example, we can postulate that some objects are more interesting than the others. We can explore feature space or parameter space like combinatorial libraries. We can define structure property relationship. For example, the relationship between the local structure, local properties, and try to minimize the predictive uncertainty. We can come up with the strategies for orchestration of multiple tools. If we have two microscopes that different microscopes that study the same object but are orchestrated by the same agent. Of course, things become even more interesting when we talk about manipulation rather than just studying the matter. So, for example, we can make electron microscope to make atoms move in certain direction and therefore assemble structures on the atomic level. But manipulation tasks are obviously more complex than the imaging tasks. So let's start with imaging. So, as I mentioned, we worked on the automated microscopy for a long time. So can we take everything that has been done before and interpret it in the context of the reward functions? Turns absolutely. So for example, we started with experiments such as taking the data and use the DCNNs to do the segmentation. So this is how the data looks like. This is whole, this is graphene, these are silicon atoms. So we can do the DCNN segmentation and find carbon and silicon. So obviously we want to do it in real time. That was fairly complicated. So it took us 5 years to figure out how to use the ensemble networks. So then we can analyze the data in real time, and we can do the same thing for the scanning probe microscopy. But there is a problem. The deep convolutional network are supervised, meaning that we need training data. They're generally not robust, even if they're ensembling. That's why we don't really have the autonomous driving still. They're black box. And then we asked ourselves a question. Can we, instead of using the deep convolutional network, somehow start with the use of the reward function approach? How would we do that? So we look back at the history. How did people find the features before there was DCNNs? And the answer is they did it using something very simple, like a Laplacian of the Gaussian. Why did they stop using Laplacian of the Gaussian? Because it's not robust. It's not that many parameters, but if you want to apply it for the imaging data, you need to tune them, and that takes quite some time and effort. So the question is, can we represent the tuning of the log as the optimization problem? Yes, we can, if we choose the reward functions. Where would the reward function come from? So in atomically resolved imaging, the obvious reward is the number of atoms that is detected in the image and the distances between these atoms. So we can formulate the reward function, and then we can find the atoms by tuning the log in the four-dimensional space of the tuning parameter. So to our surprise, this is a relatively simple workflow, but it worked remarkably well. And I wouldn't call it benchmarking, because in this case, we are the group who proposed the workflow and proposed the benchmark. So, I mean, we obviously cannot be objective about benchmarking our solution against our solution on the benchmark that we proposed. But if we still try to do the simple check for how well this algorithm behaves, it turns out that if we have the ensemble network and the simplified approach actually works better. It's more robust. And the great thing about it is that it is now unsupervised machine learning. So we don't need to train the network. We can just deploy the algorithm. And what you see is the example of our team sitting in front of the microscope when the instrument collects the data, sends the data to the HPC environment. We run the notebook that runs this optimization workflows. Basically, we segment the data in the real time. That was super interesting because transition from the supervised, not robust ML to the unsupervised, explainable, and robust is actually a big thing for active learning. Then we asked ourselves a question, would it work for more complex problems? So very often we have to work with the image analysis. When we start with the image, we can find and classify all the atoms, but then we want to find some factors of variation inside the material. For example, we want to find the radiation damage or ferroelectric domains or what's not. And typically the way we do it is we build the descriptor centered of atom, which is just a patch of the image. So it can be pretty high dimensional, like 1,000. And then we go through the set of transforms, identity or radon, Fourier, some form of clustering and dimensionality reduction. And then what we visualize is some form of component or loading maps. The problem is that with the workflows like that is that they can be depressingly long, and also they are not myopic. So that the way that we choose the descriptors at this stage and transform in this stage will affect how the end result are going to look like. So practically, a lot of people who do image analysis microscopy do that, and they spend weeks to figure out the right pathway. So we asked ourselves a question, can we use the reward-based approach for image segmentation, where essentially we have a physics-based reward function, and then we try to optimize in the combinatorial space of possible operation and the parameter space of which operation? Turns out that it actually works. So in the cases when we have the ground truth, for example, we explore simple problems like building the, finding the ferroelectric domains. So if we try to do it by clustering of the local descriptors, we can get the answers which are very close to the ground truth. And we can get the answers which are clearly incorrect. So there is too high noise or too many domains and so on and so forth. So can we do it using the optimization? Absolutely. It turns out that if we define the...
Sergei, I have a question here.
Absolutely.
So there's a human in the loop here that inspects the quality, or is it through computer vision, or is it fully automated? Are we in the semi-automated phase now?
So we have the human in the loop because the reward functions can be defined before the experiment. So from this perspective, it is automated. But once we write the workflow, we get the Pareto front, and we can choose where you want to be on the Pareto front.
Right, but the Pareto front is non-convex. How do you deal with it?
That's exactly where we have the human in the loop. So
I
if
see.
the
But you avoid the, okay.
that's exactly the trick, that we provide the reward functions, but based on physics or the heuristic, and we assume that we know them well enough. But at the same time, we say that we don't know them perfectly. So we allow the human to choose the right combination. If the reward function is known exactly, then we don't have need a human in the loop. But if the reward function is known approximately, then we do have a human in the loop.
Okay. Yeah, thank you.
And then becomes super interesting because we start to go to the point of how we define things like linear, right? So in mathematical sense, linear is defined very well, but for physical image, it's a little bit more complicated. And I'll show you how we can deal with this in the long term.
Yeah.
So another example of the automated experiment where we want to learn something is the physics discovery. So notice that typically discovering physics in microscope is fairly difficult because that's kind of not what the microscopes do. But there are special type of experiments where we can actually learn a physical law. And simple example of this experiment is the polarization switching in ferroelectric material. So you have scanning probe microscopy tip, it touches the surface, you apply the bias, material switches from polarization up to polarization down. All you do is you measure the size of this form domain. So it turns out that if you analyze the possible physical mechanism of what can be the rate limiting step, we can say that the size of the domain formed below the tip can be controlled by the thermodynamics of the process. It can be controlled by the pinning of the domain wall moving in the random media, or it can be controlled by the charge injection from the surface to compensate the depolarization fields. So what we can do in this case is to build our hypothesis space. So I would be, by the way, exceptionally interested in using LLMs and symbolic, neurosymbolic type of AI in order to build those automatically, because these are 4 hypotheses which took me about 2 months to build, despite the fact that I've worked in this field for 25 years. So it can be probably done more efficient. But once we have the hypothesis in the symbolic form, what we can do is to run what we call a hypothesis learning. So we choose the region of the parameter space for the experiment. We take the measurement. We provide the measurement result to our ML algorithm. And based on this experiment, we do 2 things. We update the parameters of our models, and we choose the model that we expect is to be the most correct one. And then we let the model that is most correct, so which allows the most rapid decrease of the predictive uncertainty, we let it choose the next experiment. Of course, we let other models to try as well, so it's usual epsilon greedy type of approach. But the important thing is that this is how it looks like. So what you see on this screen is the ferroelectric domain, is just a blob in the center. So this is the position of our probe. This is our laptop that runs the algorithm. So what you see is how the probe goes to the certain location and applies the bias pulse. So we have only 2 parameters, so bias magnitude and bias length. Then it applies the bias pulse, it creates the domain. Then you scan this region, so you see the domain that has been formed during the process. And then after we image the domain, the algorithm is going to estimate the size of the domain. So this is obviously trivial because it's just a kind of almost binary object, even an experiment. And then 2 things are going to happen. So the algorithm is going to choose the parameters of the next experiment. And while the laptop is thinking, our probe is going to essentially delete this domain. So we prepare the space for the next experiment. And this is how it looks like in action. So this is our exploratory parameter space. This is how the algorithm chooses next experiment. And this is how the algorithm figures out which of the models is the correct one. So you see that after 40 experimental steps, the model number 3 ends up to be the correct model. So why is it interesting? So there are a lot of people who talk about AI for science and come up with ideas that AI can do science without humans. So far, all of these realizations have been purely in silico. So what you see here is the relatively simple ML agent, which we informed by our own hypothesis. However, this hypothesis represents the full set of possibilities, so they're mutually exclusive, and jointly they describe the full set of possibilities for the system. And Microscope runs the experiment to figure out which of those hypotheses is correct. So we argue that this is a case of experimental ML-driven scientist. So what would be our ideal ask from the ML community in this case? So how do you build this type of hypothesis for specific experimentally realizable scenarios? So foundational models and theory are great, but practically we have experimental constraints. So how you map the overall range of opportunities to what can be done in the specific experiment is a super interesting problem. And at least by now, I'm not aware if anyone actually works on this type of things. However, we can do this type of things for more complex experiments. So this is the example of the combinatorial library. So combinatorial library is essentially a cross-section through the phase diagram, but it's a material cross-section. And this combinatorial library is a library from ferroelectric to non-ferroelectric material. So this part is rhombohedral, this one is orthorhombic. This one, nobody knows because these two phases are crystallographically incompatible. So we can use scanning probe microscope to measure ferroelectric properties. And what you see here looks like a simple Gaussian process. And it is a simple Gaussian process, but each point comes from experimental measurement. So what you don't see on this graph, because it's just a representation of the result, is that the microscope goes to one location, tunes the microscope, takes the measurement, goes to another location, tunes the microscope, takes the measurement, and this is the result that it produces. So what else can we do with the reward concept? So it turns out that a very common problem in the material science is the discovery of structure-property relationship. So very universal problem in biology, we have quantitative structure-activity relationship. So any field has it. So how can you do that? Turns out we can do it using the deep kernel learning, and this is also a reward-driven concept. So we start with all the structural information. So we have all image patches. We take the spectroscopic measurements one by one. This is sequential. We train the model that learns how to build the relationship between the structural patch and the certain characteristic of the spectrum, for example, area under the loop. And if you do that, then you choose the next location based on your policy. For example, either expected highest area under the loop, or something like upper confidence bound for it, or something that allows you to balance uncertainty and prediction. This also works very well. So look, this is the number of experimental steps. In the beginning, the microscope was exploring these locations, and then it found that the locations with the high loop area are sitting on this domain wall, and we can rationalize why it is the case. If we choose a different criterion, then we found a different domain wall. So this works. And then we started to realize that we have to be a little bit careful. So for example, this is another type of automated experiment when we want to find the local nonlinearities. But in this case, you can see that our instrument explores the parameter space, but then it starts to get trapped in this location. And maybe this is because this is the most nonlinear location, or maybe because this is just some form of metastable minimum. For a different material, it's rather obvious that it kind of sticks either here or here. So what's going on and what can we do about it? So,
Sergei, can you answer another question, because I'm
sure.
trying to guess the complexity of this problem in terms of let's say the machine learning problem, because I saw one-dimensional Gaussians, and here I see a 3-parameter function. Is that or we're talking about high-dimensional
This is fairly high dimensional. So this is a
right. That's an image. That's an image. So it can be with a
Yep.
CNN, right? It can be done with a CNN. Is that what you're showing, basically?
Yep. So the input is something like we typically take patches which can be something like 40 by 40 pixels. So
Right.
the input is 1600. Then you have the DCNN type of block that
Right.
compresses it to typically two-dimensional latent space. And then we have a Gaussian process that operates on top of this two-dimensional latent space and gives one-dimensional target function.
Okay. Got it. Got it. Thank you.
So the reason why we are doing it is, remember that my background is experiment and all my colleagues are experimentalists. So we are not, we kind of understand the experimental constraints, but with the machine learning, we always start from the simplest type of realization.
Yeah, no, I was just trying to see, you know, because because you use Gaussian processes, Gaussian processes cannot scale well, but you just answered my question. Basically,
okay.
you compress it and you go to a low dimensional space and then you deal with it.
Exactly. The important thing, however, is that the Gaussian process and the DCNN are trained jointly. So the easy way to do something like this is to take the data, compress it with the variational out encoder, and then run the Bayesian optimization over the latent space. But in this case, the latent vectors are based only on structure. For deep kernel learning, they're based on the structure property matching, not only on structure.
Okay.
So, and then it turns out that this type of behavior appears for all other problems that we have. So when we try to optimize the imaging or combinatorial library or structure property relationship, we always have to understand what the reward functions are and how to make them work together. And then we realized one very important thing, that we actually even have a patent on that, which basically submitted about 2 years ago, when we define what is the human in the loop interaction and how it can be realized. So we realized that if we just set up the automated experiments, then the reward functions and policies are defined in advance. But we don't know them precisely, right? There is always uncertainty. So it's roughly the same thing as choose the direction of the car on the road, press accelerator, but not turn the wheel. And then we asked ourselves a question, can we do better? And then we realized that it's actually a very interesting development that about 10 years ago, there was this paper by Nando de Freitas, who basically rekindled the experiment in Bayesian optimization. So that was the time when the things like Botorch started to appear. So basically the Bayesian optimization became available to the people not with the CS background. And over the last 2 years, there has been tremendous concern about the potential side effects of the AI. And a lot of the side effects are related to the alignment problem. So essentially, alignment problem is the fact that the short-term rewards that the AI algorithm can follow may be inconsistent with the long-term human objectives. And then we asked ourselves a question, do we have this problem in the automated experiment and what can we do about it? And then it turned out that we are operating in the totally different part of the real world than the classical ML community, because when we use ML to run the experiments, we are building it in the field where all the experiments before have been built by humans based on human orchestration and human observation, which means that we have the native tool to observe the progression of the experiments, for example, the real space trajectories in the latent spaces of some form, like feature spaces. We can build the tools to observe the training of the machine learning agent, for example, the decrease of predictive uncertainties and so on. And then we can naturally build the human in the loop, because at each step of the myopic process, we can define what is our physical target, so what is our reward function, and we can change it during the experiment, and we can change the behavior of the machine learning agent, so we can make it more curious or less curious. And that was really cool, because currently all the instruments, all the microscopes in the world operate with the human observing the imaging and spectral data, and issuing the basic commands to the microscope. So what we figure out is that if we have the setup with the machine learning agent, then machine learning agent issues the commands to the microscope and collects imaging and spectral data. And human, of course, can intervene and monitor, but generally what the human does is human observe the outputs of the machine learning agent and intervenes on the rewards or the policies. So reward-based concept work, and the best way to align automated experiment with the human is to give human the opportunity to dynamically change the rewards during the experiment. Now, what is the gain here? So how it is different from the classical instrument operation? And the answer is very, very simple, that many microscopes are much faster than humans. So electron microscope can generate data in the milliseconds. Humans can react much and make decisions much slower. So obviously when I see my kids playing Smash Bros or Doom, I have the impression that they can react on the, let's say, 500 millisecond time scale, maybe even 200, but definitely not 1 millisecond. And the same thing, human mind can operate with only with the relatively small images, something like 2000 by 2000 pixels. Microscope can give 30,000 by 30,000. So the ML agent essentially fills the gap in terms of latencies and data sizes that human cannot operate with. So we know the value immediately. And then we also realized that we thought that automated microscope would be moving from Toyota to Lamborghini, but it looks like it's more like going from riding a horse to driving a car. So the goals are the same, but the way that you interact with the system is totally different. So just to show you a few more short highlights. So if the reward concept works for single experiment and allows us to expand it to some new directions, can it do something fundamentally new? And then it turns out that we are going to the area where we largely speculate and maybe have one or two proofs of concept, that very often we have a challenge of saying having the same material system, for example, 2 copies of the same combinatorial libraries, or 2 versions of the same reactor that can produce different compounds or compositions, and we have different characterization tools. So the question becomes, how can we orchestrate 2 characterization tools simultaneously, and what's the value gain here? So why doing it simultaneously would be better than doing it separately? So it turns out that this becomes already very complicated, because that's not something that we can do by the simple Gaussian processes. So we either need to go into the multi-fidelity schemes, or we need to go in the multitask schemes. So for example, if we have a system with some latence, we want to be able to emit the observations of the spectra or images from this latence, and we want to train this as a GP in the parameter space, and then the decoders into the observation space. This is complicated, so that goes beyond what my group can do. So what we did was to hack the approaches, the simplifications, where rather than training the whole model, we basically use the latent space of the autoencoder and train the multitask Gaussian process on top of the latent space of the autoencoder. So this is the example of how it works. So this is 2 types of measurements. One is hysteresis loops, another is the Raman spectra. So the dotted line is the ground truth, the solid line is the surrogate model, and the dots are the measurements. So you can see that over the relatively short campaign of the 25 experiments, we basically reconstructed the whole set, and original set was 1,000 measurements for one, and 1,000 measurements for one, and 100 measurements for another one. So there is definitely a gain for individual measurements. It's a good question how to, we are not sure exactly what is the best way to benchmark the joint gain of doing it together, but it's doable. So another thing that we're working on now is conjugation. So trying to explore the running the theory and experiment in the loop. So this one is super complicated because most of the time theory and experiment simply deal with the different objects. So for example, the molecule in the theory representation and the solution would be roughly the same, but silicon crystal in theory and silicon in the real device would be very different. So we can co-navigate only if we somehow remove the epistemic uncertainty between the objects and between the results of the experiment. But the model that we're experimenting with is to having active learning model in experiment, active learning model in the theory, and the outer loop that basically steers the theory through controllable parameters until it matches the experiment. So it worked once. I would be very curious to see if it works for something more complicated other than relatively simple models. So that's interesting. So just to kind of wrap the presentation. So big data and associated infrastructure is super useful and sometimes efficient. And it is useful and sufficient in the fields that are already established and have plenty of real downstream applications. If we do science, we typically want to go where no one has gone before and do things that are new, which basically means that we typically don't have a lot of data. In fact, it actually means that we don't have it. And the question becomes whether the reward functions can be the right way to go into the unknown, because we don't know what we are going to find, but many human decisions are based on the heuristics and the past learning. And this is something that can be often represented in the reward functions. And if it is represented in this way, that can be made a part of the autonomous discovery loops. So for the few examples that we worked on, that seems to be the case. And then let's assume that we jump 10 years in the future and the autonomous tools, reward functions, and so on become a part of the science work. So how would this future look like? So in this case, it almost feels like it will become a World of Warcraft game, because you have a collaborative environment between humans and the AI. There is a specialization of roles, there are quests and objectives. So you grow in terms of skills and experience. So it starts to look like World of Warcraft. And maybe it is not as out there as it feels, because quite a lot of my colleagues who work in the field of the self-driving lab basically feel that gamification would be a part of the process. And we also know that humans like games much more than many other things. So thank you very much for attention, and I would be happy to take any questions in the remaining time.
Great. Thank you so much, Sergei, for your nice presentation. Do we have any questions from the audience?
Professor, this is Nikhil. I'm a PhD student and work with Professor Kalinin. I have one question on your modern ML side. So I'm guessing you will be dealing with varying resolutions when you scan. I guess when you use the when you collect the images, how do you deal with your different resolutions you will have in your model?
So that's a big problem, because if you look at objects and the microscopes, you have a lot of control knobs, right? You have the resolution, you have sampling, you have different form of image distortions, which are instrument specific, which basically means that the same object can look slightly differently depending on the conditions. So for me personally, my background is scanning probe microscopy. I moved in about 2015 for when it became clear that deep learning is a career and not a hobby. I spent 5 years working almost exclusively on the electron microscopy data sets, exactly because in electron microscopy, we look at the objects on the atomic level. And the atom is an atom. So the system comes with a very strong inferential biases. And even for detection of the atomic objects, it was quite a challenge to build the solution that scale, that don't break when you change resolution or sampling. For the mesoscale objects, it is almost impossible because all mesoscale objects are different. And in principle, the reward function concept, reward approach concept was born exactly because we noticed that human operators of the instruments learn how to optimize image parameters after about half a year of training. But all images are different. So human mind somehow selects something about the imaging process that is transferable, but is not based on the same data. So then we started that if it is the key, then we need to figure out what is that the human pay attention to. And if we can formulate that in the algorithmic form, meaning the chunk of the Python code, then we can use it as the reward function and optimization. And it turns out that this approach works. But you are right that the database strategies don't work because all objects are different. You simply don't have data.
Thank you. And I have one more question. I'm guessing you will also have noise when you collect the data, like some which is you want me. How do you deal that with the noise will upload in the images?
I mean, easiest way we can collect the image twice. So we expect the image to be the same and noise to be noise.
I see. Great. Thank you. It was really good talk.
I have a question, Sergei. First of all, great talk. We actually did something similar but very, very simple. In fluid mechanics, we developed with colleagues from MIT, the MIT Intelligent Towing Tank. There's a paper in Science Robotics where we show that in the field of vortex-induced vibrations, for example, in engineering, the PhD student who built this robotic water tunnel, in 6 months did more experiments, 100,000 experiments, than the entire history in the field. Typically, a PhD student would do 500 experiments, and he did 100,000 experiments in the first 6 months. And we were using Gaussian process regression to find the next point, but it was very specific. The quantity of interest was very specific, not like in your case where it's hard to tell what's the metric of success. There we're basically trying to complete the response versus the excitation phase diagram, let's say, right? So Bayesian optimization using also acquisition functions was obvious and so on. But so here's my question in your problem, which can be high dimensional as you described it. What's the advantages or disadvantages of using Bayesian optimization versus reinforcement learning, offline or online reinforcement learning? And there's many versions of reinforcement learning now.
So practically, all the problems that we have are decision problems, right?
Yeah.
So generally, for the decision problems, we kind of being realists, we want to use the simplest method possible. And if the reward function is available in a myopic way, meaning on every step, we will just go for Bayesian optimization all the time. We can build the surrogate models, which are more complex than the Gaussian processes or structured Gaussian processes. But ultimately, for physics problem, SGP plus Bayesian optimization works like a charm. Reinforcement learning becomes necessary when you have the more sparse reward function, so you need to perform several steps. And in order to use the reinforcement learning, we simply need to have the more data than for Bayesian optimization. So for Bayesian optimization, if we specify the priors, then we can just start to work with essentially 0 data or 1 seed data points. RL is much more requires much more data. So in order to use it, we first of all need to learn how to build the multi-step workflows. Secondly, we need to learn how to define the rewards. And third, we need to learn how to initialize them so we don't learn from scratch.
Yeah, so, I mean, in terms of the rewards, I thought that reinforcement learning is easy to accommodate awards.
No, that's exactly the problem, George. Okay. The thing is that, so we had a collaboration with the folks in the Google Brain for 2 years and the Mark Bellemare group before he moved. And I tried to pick up a little bit on the reinforcement learning. And then after kind of experimenting it for some time, I just asked the question, like, which is absolutely obvious. When you have a reinforcement learning problem, where does the reward come from? And then, so I don't get this part. So am I stupid? And then they started to laugh at me and said that, Sergei, you actually hit the nail on the head. The most difficult problem in the reinforcement learning problem is to describe the adequate reward function, because if we operate in the computer game space or some form of the idealized spaces, the reward function is already made for us. To be honest, I think that one of the things that kind of got a little bit out of balance was that reinforcement learning after mu0 and so on is super popular. And the people use the reinforcement learning to solve a lot of problems which are simply should not be solved by reinforcement learning, like the car pole or the mountain car. That's a model-based predictive control problem, but it's not necessarily a reinforcement learning problem. But that stays within the stochastic planning community. But for the experimental sciences, it turns out that the trick is how you define the reward. And for me as a domain scientist, in almost all cases to date, I was able to, instead of having the sparse reward, I was able to create a myopic reward. So it is very difficult. So of all the problems that I encountered in the automated synthesis or automated characterization, most of the problems cannot be solved because the objective cannot be mapped on the reward function. So machine learning just does not apply. Most of the other problems can be solved through the myopic optimization. So the reward function is defined every step. And for the time being, I have only one or two cases when we have a scenario when there is a sparse reward, meaning that reinforcement learning works, but the myopic optimization doesn't work very well. So that's actually a very, very interesting thing. And that's why when I show this triangle where there is virtually nothing between the simple rewards and very complex objective, that's what I mean. It's very empty space for now.
Yeah, I appreciate that triangle. Was very interesting to show the remote target versus the...
But that's the beauty of it, because if we learn how to design the reward functions, then two things happen. First of all, if we design them, we can test them rapidly. And second thing, if we have a reward function, then all problems are optimization problems, and we know how to solve optimization problems.
Yeah. Great. Thank you very much. It was an unusual talk, but very thought-provoking. So thanks for taking the time today.
Thank you.
Thank you so much, Sergei. Thank you so much for your time.
Bye.
Hi, Luyuan. You're here, but I can see you turn on your camera.
Hi, Ken.
How are you doing?
Fine. I'm fine. Can you hear me?
Great. Yes, I can. Could you please try sharing your screen?
Okay. I'm trying to do it. Is that all right?
Yes. Could you please put it in presentation mode?
Okay.
Yeah, great. So first of all, thank you so much for joining us. I know that was a bit later, so thank you so much for your time. And now, well, we have a second speaker today. His name is Luyuan Ning. He completed his PhD in engineering at Shanghai Jiao Tong University in June 2024. His main research areas focus on structural strength prediction and data-driven computational mechanics. The main works include heterogeneous structure strain and crack simulations by finite element methods, very dynamics, pings, and data-driven neural networks. He has authored many SciI journal articles, which have been published in CMAME, the European Journal of Mechanics, Solids and Ceramics International, etc. Luyuan, once again, thank you so much for your time today. And with this short introduction, you can begin whenever you're ready.
Okay, thank you for your introduction, and thanks for the invitation from Professor Kaniadakis to give me such an important opportunity. Hello, everyone. It's my great pleasure to give my presentation in Crunch Group. And the name of my presentation is Physics-Informed Neural Networks for Strength Prediction in Heterogeneous Plate. My name is Luyuan Ning. I'm a doctoral student just graduated from Shanghai Jiao Tong University under the guidance of my supervisors, Professor Yingzhen Liu and Professor Weizhe Wang. The presentation is divided into the following 5 parts. It starts with a brief introduction of the research background and our related works. The following 2nd to 4th part is our work about the pair dynamic informed neural networks for displacement characterization or crack simulations. There are 3 types of the network. Heterogeneous structures widely exist in engineering problems and scientific problems. For example, particle reinforced coatings and fiber reinforced composites are synthetic materials to obtain special property by its special structures. And in contrast, material with inactive evolutions are the heterogeneous structures that we should passively study with. Heterogeneous structures vary not only with the process parameter, but also with the manufacturing batch. Although the traditional methods like numerical or experiment methods have achieved a considerable success in structure strength evaluation, such variable structures makes the traditional methods should reconstruct the analysis model each time. As a result, the traditional methods becomes time-consuming. So, for example, the image restoration model often costs over an hour, and the experimental methods can reach to 1,000 hours. In this case, we established a pix-to-pix CGAN-based rapid prediction model for the inclusion structures. As we know, the pix-to-pix model is good at pixel level transformation. And we found that the stress distribution is significantly related to the structures. So the pix-to-pix model is applied to implement this task. The training data set is obtained by the image restoration FEM. By this way, we directly predict the stress distribution of the structures with a high efficiency. And the prediction speed is about 100 times faster than the FEM. But there is a distinct disadvantage of this model. The data dependence of it is too high. So we have cost plenty of time to set up the training data set. And sometimes the prediction results is unreasonable. So we embedded the elastic mechanics into the loss function of the pix-to-pix model. This time we predict the strength distribution of the structure. We use deformation compatibility condition to constrain the reasonability of the strength distribution and the constitutive laws to constrain the quantitative relationship between the strength components. Finally, we got more reasonable predictions. As the figures show, we can see that there are less noise, like the compared to this one, there are less lattice noise and distinctly lower decision error. Accordingly, the prediction accuracy of EMI gain is higher than that of the pix-to-pix model under the same training data set. However, the properties in heterogeneous structures exist in discontinuous.
Can I ask you a question? Can you go back to, I want to see the errors. So The emigun is the one that includes the mechanics, right? The physics, the laws.
Oh, yes, yes.
And what are you plotting here? These are errors in what? In strains, in what stresses, what displacements, what errors are these? The errors that you have, no, the errors that you have on the table on in the red boxes. What is the error? What is the metric? What's the quantity you are comparing?
Oh, this is a local magnification of the strain distribution. You means that local magnification image. The color distribution is the error of the deformation compatibility condition calculated by the difference form of the equations. This one is the error of the FEM results. We can see that it's nearly zero, and that one is the peaks-to-peaks predict the results. It's full of noise.
What norm do you use? Is it the L2 norm, the average norm, or the energy norm? What norm are you using to compare to find these errors? Error is point-wise, but you report 81.09% error in E22. Is that in a patch, in the whole image? Is it L2 average?
You mean in the table?
Yeah. How did you compute these errors? Yes.
This is the low. I'm sorry. I should adjust the window. This is the low error area. This is the percentage of the low error area among the integral structures. We define that the error lower than 3% of the real number is the low error area. So we count the average performance of the peaks-to-peaks model and the AMI gain, and compare the low error area percentage and show it in the table.
Still don't understand. This cannot be errors. These are something else.
So it's
it's
like you compute the point-wise error for the whole image, and then you select the points where the error is less than 3%. So then there will be, for example, 68% of the data that you have has the error less than 3%, something like that.
Yes.
I see. Okay. So you identify regions with low error. I got it. Yeah.
Okay. Can I continue? Yeah.
Please.
Considering a homogeneous bar on the tension, the displacement in it is all derivable. Differently, in the heterogeneous bar, the displacement near the material interface is non-derivable because of the abrupt change of the material property. So it is difficult to be globally described by PDEs, so as to the PDE constrained neural network. We need domain decomposition to describe it with PDEs. That can be represented by the results of our investigation. You can see that even the FEM results, the DCC error calculated in difference form in the individual material phase, they are nearly zero. But there are distinct noise near the material interface. You can refer to this structure image. So we modify the discriminator to simultaneously discriminate the truth of strains and the DCC error. This phenomenon shows that we need a better or more general equation to constrain the network for the heterogeneous structures. Then I will work about the pure dynamic informed neural networks for displacement characterization or crack simulation. There are three types of the network. In the year of 2000, Kalinin proposed the non-local pure dynamic theory. In bond-based PD, an elastic body is divided into a series of material points, and each central point, xk, interacts with other material points within its non-local horizon, hxk. So the PDEs in classical mechanics are replaced by the integral differential equations. As the horizon moves from left to right, we can see that the different material properties are being smoothed, as there is the ideal number of the discrete material points, and the displacement near the material interface are becoming derivable. According to its non-local interaction, the PD has successfully applied in many engineering problems, such as the fracture strength prediction of composites and the failure mode simulation in eroded coatings. We can see that the predicted mode is similar to the one that obtained by the experimental tests. Considering the advantage of PD, PD-informed neural network is established to characterize globally characterize the displacements in heterogeneous structures. In this structure, the FDN is directly informed by the PD equations, so the PDs are replaced by the integral differential equation. Then the higher order derivatives in the PDs are avoided. So it can globally describe the displacements both in homogeneous and heterogeneous structures. I should say that the integral differential equations in PD are more represented non-local interaction is more complex than the PDs in classical mechanics. So they directly fine sampling will induce plenty of training approaches and too much training time. So a gradual refinement sampling method is applied to accelerate the convergence speed of the network. By sampling from coarse to fine, we can see that the total loss of the network decreased more rapidly than that of the network trained by directed fine sampling. This is equivalent to transfer learning from coarse accuracy to fine accuracy. Then we first applied the PDI into a homogeneous plate to validate its displacement characterization accuracy. The plate is clamped on the left edge, and the right edge is subjected to a linear change the force boundary. And we can see that compared to the PD numerical results, PDIN can well characterize the US and UI of variation trends. For the application of PDI in heterogeneous plate,
I have a question for the,
Okay.
for the previous test.
Okay.
So, right? That's what you show here.
Okay, you mean this slide?
Yeah, this slide, yes. The accuracy is comparable between numerical and the neural network, but how about the speed?
You mean the calculation speed?
Yes.
Time? Yeah, the computational costs. I should say that by this way, the solving speed is slower than the PD numerical method.
How much slower? Twice, 3 times, 10 times?
Maybe over 20 times.
20 times. Okay.
Okay.
Yeah. Okay.
But we've recently found that in the fourth part, the PD potential energy informed neural network has a good solving speed in especially larger scale models, and I will explain it in the last part.
Okay. Thank you.
Okay. So I will continue the heterogeneous place. Since the basic network is FCN, in this plate, with Bunny inclusion, we can randomly sample the refinement points near the material interface to enhance the nonlinear fitting ability of the PDIN. The body plate is clamped on the left edge, and the right edge is also subject to a linear chain force. We can see in these figures, compared to the PD numerical results, the general variation trends are well characterized by PDN, and the displacement extracted from the diagonal line shows that the local refinement sampling has better performance in nonlinear displacement characterization, especially near the complex ear interface. Next part is our work about the peer dynamic informed convolutional neural network. Traditional pins conduct the solution in the given domain. That means training is the solving. So it is a time-consuming procedure, as you have asked. And sometimes it even slower than the traditional numerical method. So we established a PD-informed unit, convolutional neural network to obtain generalization ability near the training data space. The CN is established as a unit. Since the unit is constrained by the purely PD equations, we only have to establish a series of heterogeneous bars with different section properties and force boundaries to establish the data set. That costs a little time. By minimizing the PD loss, it is expected that the unit can directly predict the displacement in different, especially auto sample bars. Here is the training loss of the PDUN. You can see that the purely PD-driven loss of a convolutional neural network can be minimized by backpropagation accuracy. Finally, the application of PDUN shows that the purely PD constrained network can well predict the displacement of the different bars in validation group. We can see that the bars are different with section properties and section forces. That means that the PDUN can possess generalization ability in the training data space. However, the current study is successfully conducted with one-dimensional bars. The prediction is very efficient, costing about 10 milliseconds each case. However, in the 2D models, we use the random structures and different linear force boundary to constrain the structure. We can see because of the extremely slow convergence speed of the PDUN, finally the training network only predicts the coarse variation trends of the plates. I'm trying to optimize the framework, including your famous deep operant learning, and I will shortly briefly introduce it in the last prospects. The next part is the paradynamic potential energy informed neural network. As we mentioned before, in bond-based PD, each central point has a non-local horizon, and it interacts with other points with the bonds. When the structure deformed under tension, the bonds are stretched. And here is criteria for the judgment of the bond fracture. To put it simple, that is S, it denotes the elongation ratio of the bonds. When S is smaller than the defined critical elongation ratio S0, the bond maintains interaction. Otherwise, when S is greater than S0, the bond breaks. So that's the strategy of PD to simulate the cracking behavior. Noticeably, a single step of crack propagation generally slightly change the integral structure. So the displacement in the structure before and after a step of crack propagation is similar. So we can use transfer learning strategy to accelerate the solution. Based on the PD theory and transfer learning, PD potential energy informed neural network, PDEN, established to simulate the crack behaviors. Since the total energy is a weakened form of the local equilibriums, the loss function of PDEN is simplified. So the solving speed of the PDEN is much faster than that of the PDRN. In the framework, FCN is considered as the trial function of the displacements, and according to the principle of minimum potential energy, the total energy in PD form can be directly minimized by the network training. Then the displacements can be solved. Besides, by the way, the cracking behavior can be solved by the PD theory. And the following solving steps of the crack initiation and or crack propagation procedure can be accelerated by the transfer learning. The elongation ratio is calculated based on the stress distribution. So we first validated the stress distribution characterization accuracy by a homogeneous plate. As a comparison with PD numerical method, we can see that the characterization is good. After the validation of displacement characterization accuracy, we first applied the PDEN into a CT plate. In this plate, we uniformly distributed 64 by 64 metal points, and we construct the pre-cracks by cutting the bond interaction. During the training process, the total loss of the network represents the total potential energy of the system. As we can see that each time the crack propagates, there is a sudden decrease of the total energy. That means the crack propagation occurs. After the final fracture of the plate, the total energy goes down to 0. The simulation results of the city plate are illustrated in these figures. As compared with the published literature, we can see that the predicted crack paths are exactly the same. Besides, we also compare the procedure parameters like displacement crack length and force displacement curves. It shows that the integral procedure of crack simulation by PDEN is reliable. And further, the PDEN is applied into a plate with two pre-cracks to investigate its simulation ability of crack coalescence. Also compared with the published paper, the crack propagation trend is the same. In the intermediate interaction region, in the later stage, it becomes narrower, and the displacement and the strength are simultaneous increase because of the strength concentration. So it results a region break of the bonds. The aforementioned two plates both contain pre-cracks. It means that the crack simulation are conducted in the crack propagations procedure. So, however, crack initiation is also important. So we established two plates without pre-cracks to investigate its crack initiation simulation ability. The first one is the L-shaped plate. We also compare with the published papers by the numerical or experimental results. You can see that the PDEN can well characterize the crack path. Noticeably, the sampling points are uniformly distributed in the solving domain. So we don't need a pre-refined path by the prior knowledges. So we don't need a pre-refined path based on the prior knowledges to simulate the crack initiation behavior. So it is convenient and efficient. And there is a plate with a central hole to investigate the multi-crack initiation and propagation ability, simulation abilities, and the comparison shows that the result is good. In our investigation, we found that the PDEN doesn't well predict the crack length each time. For the reason, we found that the weight decay training strategy and the scale of the neuron scales of the network has a distinct influence of the results. As this figure shows that the correctly characterized displacements is strongly nonlinear near the crack. There is a distinct step between the matter points located on the both sides of the crack. Even we said that means that and as we know, the data-driven neural network usually use weight decay or other strategies to reduce the magnitude of higher order parameters to prevent overfitting. But PDEN with such strategy will lack of the nonlinear fitting ability of such strong nonlinear displacements. Even we set a weight decay parameter about 10 to the minus 4 magnitude, the total energy field decrease. The network seems just to ignore the existence of the crack. Besides, insufficient neuron scales of the network also cause wrong an error prediction of the crack length. This also because of the insufficient nonlinear fitting ability of the displacement near the crack tip. Okay, finally, the conclusion and the prospects. As we mentioned before, the integral differential equation in PD represents a more complex interaction. So the solving speed of PD is slow, both in implicit and explicit methods. The computational resources of the implicit method of PD is extremely high. And even the explicit method of PD can solve comparatively larger scale of model. The solution speed is also too slow. For the PDEN, we recently found that the framework combined with GPU acceleration has a good calculation speed of the model of the heterogeneous plates, especially in larger scale models. I'm trying to optimize the frameworks and to increase the solving speed and further apply the model into 3D models. It is expected to have a good acceleration to the solving speed of PD. Besides, continue my research work on the generalization solving based on purely physics constraints. We may develop purely PD constrained frameworks to predict the displacements by purely PD driven model. I'm trying to optimize this framework by the deep ONet framework, but combining with the advantage of PD equation, it can be applied in any different heterogeneous structures. I have achieved the initial success by the hybrid data and PD driven loss to train the network. The network with different data dependence can applied in the strength prediction and other engineering problems. Thanks for your attention, and thanks for your attention to my English.
Thank you so much, Luyuan. That was actually your English was really good. You did a really good job. Do we have any questions from the audience?
Elham, do you have questions?
For this slide, I have one question about this. You used DeepONet for discovering displacement. Could you explain, like for the previous slide, what is input, what is output, and what the purpose is here? Are you using physics in DeepONet here?
The input of the input of the branchnet is the coordinates, individual coordinates of the matter points and the structure represented by the image form, and the truncnet input is force boundaries. I also make assumptions that all of the plates is clamped with on the left edge, and the right edge is subjected to a linear boundary condition, but the force is different. So I want to refer to this structure to realize the rapid prediction of the displacements in the heterogeneous plates.
You mean, did you consider like coordinates in BranchNet and then just like multiple forces in trunknet?
Yes. Each maybe the force boundaries are different for each case. So correspondingly, so I input the structure and the coordinates of the points and the corresponding force boundaries into branchnet and trunknet. Yeah.
You have like multiple geometries, or you're changing force boundaries? I was confused a little bit here.
Yes, the geometry is different and the force boundary are different. Maybe it's difficult. Maybe it's a little different from the deep ONet.
Yes.
Yeah.
Where do you apply the peridynamics equations? I see if they're just to generate data, or is it at the end? Or you only have a data-driven loss?
Yeah, data-driven.
Yes. The loss of the structure is a combination of data-driven and PD loss functions. I want to decrease the data dependence of the framework as much as possible. Ideally, I will eliminate.
Well, it's a physics informed, so I think that's what he has in that box. It's a physics informed.
Yes. The only thing is that they like use the multiple or different geometries in branchnet. That is interesting.
Right, and also the trunk is a UNet.
Yes. Yes. Yeah.
Yeah.
Thanks for addressing my question. Thank you for your talk.
Can you say how do you compute the integrals in the peridynamics equations? Do you do Monte Carlo? How do you compute the integral? You have to compute an integral, right? The integrals that goes into a PD, into peridynamics. How do you do that? You just sum.
We calculate we usually calculate the integral in the PD equation in the discrete form.
So you have a grid, or you do it with Monte Carlo?
No. Yes. Maybe the input structure is different in each case, and we can just because the PD equation can be directly applied into different heterogeneous structures. Maybe we can directly calculate. Like there is a central point of the, and this is the horizon of the central metal point. We can directly use the discrete form of the integral differential equation to calculate the local balance of the force and the boundary balance of the surface material points. And because the generalization of because of the general ability of the PD non-local interaction, when we use the Monte Carlo method to generate different heterogeneous structures, the framework will predict assumed displacement. So we use the PD equation to calculate the truth or the physics of the displacements, the right or wrong, to make a judgment of the prediction. So by minimizing the PD loss, we can it is expected to have a better prediction of the displacements by the framework. But now I use hybrid data-driven and PD-driven loss to train the network. Actually, it is very difficult to find an efficient way to minimize the purely PD-driven loss. Maybe I can do it in the future.
Renee, do you have any questions? Renee Jiao from Stanford is joined for this talk.
George. I don't have any detailed questions now, but we can probably discuss later.
Okay.
Okay, do we have any other questions from the audience? It looks like we do not, so I think that we could close the seminar. Thank you so much, Luyuan, for your time. This was a really nice presentation. Also, thank you everyone for your time today. So I think that we can close the seminar a bit early. So I hope you all have a nice weekend and see you next week.
Yeah. Okay. Thanks.
Yeah.
Thank you.
Bye.
Thank you for your invitation, Professor Kalinin.
Yeah, you're welcome. Thank you.
I stop my sharing.